Hello friends, welcome to Abaqus Acumen for quick and sound learning. In this video tutorial, I will show you how to simulate the rolling of a thick plate, and the simulation what you see on your screen. So this is for single pass rolling process. So this workpiece is fed from the one end and it goes through this rolling stand, and the metal is being offsetted and it is being rolled. So through this kind of process simulation, we can generate a lot of insight in terms of the metal flow and the geometry deformation contour, that is a equivalent, or I will say plastic strain contour, and the displacement part, of course. So all these things we can generate through this kind of process simulation. So here we are taking the example of rolling process. Our ultimate objective is that I will describe all the steps involved for this FE model built up, like right from the geometry creation to the loads and boundary condition to, and then in the end we should be able to, you should be able to simulate and replicate the simulation by referring to this video. Okay, so I will just give you some background about this process. So let's understand the mechanism involved in this rolling process. Just to give a quick recap, like we have two rollers, and this is a rolling stand what we call, and the workpiece, okay, which is fed from the one side, which is having a cross section of, say for this example we are considering the cross section of 40 by 40 millimeter. Once it goes through this rolling stand, it is obviously it get rolled, and in the end we are expecting the thickness is reduced to 30 millimeter. Thickness is reduced to 30 millimeter, and of course there will be some spreading of the material in other direction as well. So we are simulating by considering the quarter-symmetric model, so that it will be very simplified approach, and also you will save a lot of CPU, that is computational time, by doing this quarter-symmetric model. So this is a good learning for us to how we can effectively simulate using this taking advantage of symmetry, and the same time we will have a quality result, as well as the CPU time is at minimum. Okay, here the workpiece, that is metal, is a quarter model with a size of 20 millimeter by 20 millimeter. That is it is something you imagine only this portion is considered, and the roller is being rotated with angular velocity of 6.28 radian per second and with a radius of 170 millimeter. Once it goes through this under the roller, the thickness is been reduced by 5 millimeter. So that is our ultimate objective. And then this simulation we are doing it for in the explicit dynamic condition, Abaqus explicit dynamic condition. Although we know this rolling process is conducted at or being performed at very low speeds, typically 1 meter per second, there won't be any inertia effects for this kind of rolling process. We are using although we are using Abaqus explicit, we will be considering the quasi-static, or we will attaining the quasi-static condition, so that the inertia effect will be attending towards zero. To validate the quasi-static condition, we need to keep the kinetic energy of the system at very low level, or it's almost zero. And just for our information, the rolling process can reduce the thickness of the plate up to 42% in a single roll pass, so which is a very significant reduction in the thickness one we can expect through this rolling process. And then the column friction between the roller and the workpiece is extremely important. So it is here we are considering 0.3 as a column friction, but if it happens that if the column or friction is considered less, or inherently it is in the process itself is very low, then we may expect that there will be a slip between the roller and the workpiece, and then the process won't be efficient, as well as the quality of the rolling will deteriorate. So for that we need to give a special attention, so that in the process as well as in the simulation we have coefficient of friction up to 0.3 to 0.4 through this friction. So once the workpiece is fed with initial velocity, so it will have the friction, so that will the friction force will take over and it will pull through this stand. Another important point which is to be considered, that once the workpiece is fed at the same speed of roller, the disturbance in the initial acceleration, the x direction at the contact point is zero. So what it means that the workpiece, once it get in touch with the roller, the workpiece initial velocity should be same as the tip velocity of this roller. So roller is here, it is moving with the angular velocity of 6.28 radian per second, and if you calculate with single r omega formula, so the tip velocity is around 1.067 meter per second. So with the same velocity we need to feed this workpiece so that there won't be any jerk or acceleration at this contact point. Okay, so that we need to consider in the process as well as, and we also need to replicate in our simulation. And just quick look at the loads and boundary conditions for this FE model. So as we are modeling the quarter symmetric model, we'll be applying jet symmetric, that is on XY face. So this is the XY face of the workpiece, and then U2, that is the bottom face, will be constrained in vertical direction, that is in y direction, that is u2 is equal to 0, and then we'll be considering all 1 to 5 degrees of freedom of for the roller. So only this roller is allowed only to rotate about the g-axis with the angular velocity, that is a prescribed velocity of 6.28 radian per second, and then the initial velocity of the sample. So we'll be applying the initial velocity for the sample as 1067.6 millimeter per second. Of course there will be a boundary angular velocity of our roller, so we'll be applying this angular velocity to the roller as well. So I'll write it down here itself. So unit system for this FE model is Newton, ton, second. So this is the unit system we'll be following for this FE model build-up. Let's go back and start building this FE model in AbaqusCAE. So here I'm using 6.12 version of AbaqusCAE software. So we'll start with a blank canvas, and so we'll start with making with a part, that is workpiece. Size is 20. This is a quarter model. Then we will extrude this by 92 millimeter, that is the length we are considering. This is done, and we will apply. Now we'll go to property, we'll create the material. So the material is just say material name as material 1, let it be. So this is for steel, 7.8 e raised to minus 9, that is ton per millimeter cube. And then the elastic modulus is so we'll have Young's modulus, that is 1.5 e raised to 5, and then the Poisson's ratio is 0.3, and then the plastic curve. So I have data for, this is in MPa and strain van number. So just simply copy, so paste it. So this is done. Okay, and then come back, then we'll define a section. So this is a solid section, homogeneous. Say continue, then say okay, dismiss, and we'll assign this property to this geometry. Okay, so this is done. So the workpiece is ready. Now we'll create the rolling part. So go to here, part. So this is rolling, or I'll say roller. This is analytical rigid and extrusion. So approximate side we are considering size around 30 millimeter. So this is quarter symmetric model. So I will show you how to do this. So continue and go for 3-point arc. So just this is sufficient for us, and we need to modify the radius to 170 millimeter. So we'll key in the number. It's okay, done. And we need to extrude this by 30 millimeter. Okay, this is ready, and now we'll make a assembly out of it. Okay, so guys, this is we need to do some positioning over here, so it will take some time. So for whom for those who are familiar with positioning of this parts in AbaqusCAE, they can simply skip this or little forward this video, and they can directly jump to the other loads and boundary condition and contact definitions. So now we'll translate the roller. Okay, slightly translate this as well by 5 millimeter in G direction. So now we'll do couple of definitions for this rigid body. So go to part. For this we need to define the reference point. Roller, so go to reference point, so you can choose the reference point at this point. So this is where the center point for this arc. It's done. Then we'll go back to assembly again. So guys, so now the geometry is ready, is positioned appropriately, and we also defined the reference point for this rigid roller. Okay, so if you have any if you missed any points, you can always refer a few of our videos, that is Abaqus Acumen videos, wherein we have more detailed elaborated discussions on defining this reference point and the rigid body, and also the positioning of the parts as appropriate location. So all those you can refer any of the videos, you will find out more in detail. Let me give you some more inputs. So these are the important keywords we need to consider for this simulation. So the one is the element formulation. So this is very critical when we do a process simulation. So for element formulation, for this brick element, we are considering that is a C3D8R type of element. We are considering the formulation through the section control keyword, that is hourglass is equal to stiffness, and then we will be choosing the kinematic split is equal to centroid. So these are the two important triggers we will be activating to consider this as a element formulation for rolling process simulation. And also, as I mentioned, we are considering the mass scaling factor. So this is just to attain the quasi-static condition, or I will say without we can safely attain the quasi-static condition by going for this mass scaling factor. And we also ensure that the kinetic energy, so this number we iterated, and we know for this case scaling factor the quasi-static condition is still be attained, and at the same time, so the CPU time will be less. So by doing this, we will be maintaining or attaining the level of accuracy desired, and also the CPU time will be economical. Okay, so in the end, of course, when we do once we finish this simulation, we will be looking for the output in terms of plastic strain contour and how the roll geometry looks like, and also the metal flow study. So these are the points, just to give you a heads up. Going back to the model built up process, so as I mentioned, we need to define the section control. For that, you go to the mesh module, and in that you look for element type. Okay, and so we need to make a independent these parts. So now we can do it. So go to mesh, element type, and so here we'll be choosing the explicit, and as I mentioned, the kinematic split has to be centroid, and for hourglass control we will be choosing the stiffness, and leave all other parameters to defaults. Okay, just say okay, choose the around 2.5 millimeter, or I will say 2.5 millimeter should be fine as a element size. Say mesh it, so this is done. So before we march towards the loads and boundary conditions, so we need to do one more small activity by positioning this assembly to this datum plane, that is at 0 0, so that when we do this quarter symmetric model, it will have appropriate reflective planes. Okay, so just follow and understand the activity what I am doing. So this is a very critical point when we consider or go for the quarter or symmetric model. So let's do it. So again, go back to assembly and say you translate the instance. So let me find out the distance between the points. So the distance is okay, in G direction it is -20, and in X direction it is 39.5. okay, we'll do that now. Shift, we'll bring this point to this 0 0 position, so that is the axis should be 0 0 0. Okay, so for that again we will do another operation. Shift, so this is 20 millimeter. I need to push it upward by 20 millimeter. Alright, So guys, now you can see the coordinate system or the plane is at 0 0, this point. So we'll be using this face for the G symmetry, and then the bottom face for the upward direction symmetry, so that once we do the simulation and do the post processing, we'll see the full model highlighted, and it will be more clarity in terms of understanding about the workpiece rolling. Okay, so now it's all set to go for next step. So this is one of the critical step I want you to remember and carry out at your end as well. So now let's go to the step part. So we'll be using the dynamic explicit, and here the time period is 90 milliseconds, that is in second it is 0.09. So we'll also define the mass scaling factor. As this is a quasi-static condition, we can go for some higher number. So this is a scale factor. So we already iterated and find out the appropriate scaling factor, mass scaling factor, that is 2758.5. this is a mass scaling factor. So this is a factor will retain the quasi-static condition for this simulation by keeping the kinetic energy at very low level or at zero level, and also at the same time the runtime or the CPU computational time will be at minimum. So just remember, so click on this scale by factor, and then 2758.5, this is the scale factor, that is a mass scale factor we are defining. So say OK. So this is done, dismiss. Then we'll move to the next part, that is interaction. So before defining a contact between the roller part and the workpiece, so we need to define the surface for this rigid roller. Okay, for that again go to assembly, and here I will create a surface. So just to show you again, go to assembly and look for the surface, create. So this is geometry, and I will say roller surface. Continue, select this roller part, done, and the face we'll be selecting is purple. Okay, so now we are set to define the contact. Go to interaction module, create, select this general contact explicit, continue, all with self. So here we define the friction. So already we talked about the friction, so we are considering the column friction value as 0.3. That's okay, and select this option, say OK. So this is done. So now we'll move to the next part, that is loads and boundary condition. So we'll start with the boundary condition. So the first one is a G symmetry. So you can say G symmetry, continue, and here we'll be selecting the face. So this is, remember, this is quarter model. So take this face, select this face, done, and we'll be choosing the G symmetric, applied. So you can create one more, that is for the bottom plane. So base C2, this is for bottom. Choose this displacement rotation, continue, and slightly rotate the model, choose the face, done, and here we'll be considering only the u2 is equal to 0, that is the upward translation is 0, that is this is another plane of symmetry. Okay, and create one more. So here we are defining the constraint for the roller. So this is for roller. So here we'll be choosing the reference point, and we'll be constraining all degree of freedom, and we are leaving this G rotation, and along this we are applying the angular velocity. So that is our next step. So as of now we have to constrain all these degrees of freedom for this roller center point, this reference point. Say okay. So this is done. So now we'll do angular velocity application. So continue, choose the same reference point, done. So this is V3, this is 6.28. okay, dismiss. Now we'll apply initial velocity to the workpiece. So create, this is initial velocity, continue, and here you have to select continue. So I will select the part. Okay, so this is the workpiece selected, and V3. So we need to define the in X direction. So the V1 value is, let me refer it, what is the number for it? Yeah, this is 1067.6 millimeter per second. 1067.6. This is the speed, that is the tip speed, which is applied to the entire workpiece in positive X direction. This is applied, dismiss. So we are done with the loads and boundary condition. So we already defined the element control sections. So now the job, create, and say job numbers, put some name, continue, just say okay, submit the job. Okay, so guys, we have results. Let me switch on for, okay, so we can simply animate this. Okay, okay, bingo. So we have this rolling process simulated. So we can see the how the part or the workpiece is being deformed when it goes through the roller stand. So this is a symmetric model. You can see the rollers and the piece on the other side. So we can also reflect to the in XY plane as well. So that, let me do that for you. So you go to display option and you can do it in XY plane as well. Alright, so as this is a quarter model, so we are first, so let me bring it back. So this is what you see, you might see in your screen. To see the full model for visualization, so this is in XY and this is XZ direction. So these are the two planes we already defined for the quarter symmetric. So once we trigger these mirror planes, so you can visualize the full model. So this is the more this is the more realistic rolling stand what we have, or this is what we wanted to simulate in the end. So now you can visualize the complete workpiece which is fed through this roller stand. Okay, so now you can go to the different results options. So you can start with displacement part. So you can simply see the displacement part. Yeah, this is it. So this is what 4.99 millimeter, that's what we wanted to achieve, that is 5 millimeter it has to deform. So this is done, and then we can also see the equivalent plastic strain. So this is how the strain distribution, and similarly you can go for the stresses part. This is one measure stresses. Guys, this is what I wanted to show you or take you through this tutorial, and we learned how to build the FE model for the cold rolling process simulation. Please go ahead and try this at your end and follow all the steps what has been shown in this video. And if you find this video useful, please go ahead, like this video, and also subscribe our Abaqus Acumen channel so that you will keep receiving the new exciting videos for learning. So thank you, bye bye.